Welcome back to the deep dive. I thought I understood software testing. I pictured someone clicking around, trying to break things, finding bugs. Simple enough.
The classic bug hunt.
Exactly. But diving into these sources, especially the formal documents for professional certification, it's just a completely different world. It's this incredibly rigorous, structured discipline. It's about economics. It's about strategy. Our sources for this deep dive are pretty dense, but wow, are they rewarding. We're pulling from the core ISTQB certified tester program, and we're mixing that with some key industry reports on defect prevention.
And cost analysis, which is huge.
It is. So our mission today is to really distill those core principles, the specialized vocabulary, and the actual techniques that separate, the casual bug hunter from a true QA professional. We're trying to give you a bit of a shortcut.
And that professional vocabulary is just non-negotiable. It has to be there. When we're talking about quality, we are dealing with these incredibly precise, internationally recognized terms.
Right.
The whole point of a framework like this is to make sure that when you say failure, and I say failure, we mean the exact same thing. It doesn't matter if your team is in London or Lahore.
It creates a common ground.
It's the essential first step. You have to have that to even begin talking about strategic quality.
Okay, so let's start there. I want to tackle a huge myth right at the top. The idea that quality assurance, QA, and testing are the same thing. I hear them used interchangeably all the time.
All the time, and they are absolutely not.
So for someone new to this, what is the practical difference?
It's vital, and it's all about timing. Think of it like this. Testing is reactive. It's the thing you do after the code is already built. You're running the software, you're looking for the bomb that's already been planted.
Okay.
Quality assurance, or QA, is proactive. It's the architectural work. It's about looking at the entire development process itself, the plans, the methods, the documents, and making sure they are so good that the bomb was never built in the first place.
So QA is the preventative medicine, testing is the diagnosis and treatment.
That's a great way to put it.
And that idea seems to drive this whole shift-left philosophy we hear so much about, moving that quality focus way earlier. Does that mean a QA specialist should be in the room from day one?
From minute one, absolutely. Shift left means they are involved right at the requirements gathering stage. And they're not just thinking about the happy path, what happens when everything goes right.
They're thinking about what could go wrong.
Precisely. They are designing the system around the unhappy paths. They make sure all those negative scenarios and error handling rules are fully defined before a single line of code is ever written.
And the reason the big driver for all this early intervention, it really just comes down to money. The cost data in these reports is it's staggering.
It really is.
One report from the IBM Systems Sciences Institute says the cost to fix a defect found after release can be up to 100 times as much as one you find back in the design phase.
100 times. It's an enormous penalty for delay. And we see it in terms of raw effort, too. Another report found that fixing one bug in production takes, about 15 hours of work?
15 hours. Compared to only 5 hours if you catch it while you're still coding.
Exactly. 3 times the effort.
So here's the question I want to unpack. How do you sell that proactive QA cost to management? Because, on a spreadsheet, that early QA investment looks like an upfront expense.
That is the strategic conversation you have to master. You have to show them the data on where defects actually come from. You point out that a surprising 64% of all defect costs originate not in the code.
64%.
But in the requirements and design phases. The error was baked in months ago. If your blueprint is flawed, waiting until the house is built to test the foundation is just fundamentally inefficient.
It almost sounds like that Greek myth, Sisyphus. You're constantly rolling the software up the hill. You find a bug, a fix goes in, but then that fix might create a new bug.
And the rock rolls back down.
The work is never truly done. But if we accept that, the only way to win is to be incredibly precise about what we're fighting. So let's establish that rigorous professional language.
That precision is everything. Especially with the defect chain. A professional has to be able to break down every major issue into its parts.
Okay, walk me through it.
Let's use a simple scenario. A developer gets distracted by their phone ringing. That external event, that's the root cause.
The phone call.
Right. Because of that distraction, the developer makes a thinking mistake. Maybe they misread a requirement. That mental slip-up is the error. Then that error gets put into the code as faulty logic. That is the defect, the bug.
And then when I, as a tester, go in and the system does something it shouldn't, like accepting invalid data, that observable incorrect behavior is the failure.
Exactly. So you see, for true prevention, you can't just fix the defect. You have to trace it all the way back. You have to ask why that error happened and what the root cause was to stop it from happening again.
So it's an intellectual exercise.
It is. Which is why professional testing demands what they call the K3 or apply level of thinking. You can't just remember definitions. K1 is remember, K2 is understand, K3 is applying it to a new situation. That's why most of the certification training is on techniques and management, not just vocabulary.
So less glossary, more strategy.
Mhm.
And speaking of strategy, one of the core principles for focusing your effort is that defects cluster together. Why is that so powerful?
Oh, it saves an incredible amount of time. It's basically the Pareto principle. You know, the 80-20 rule.
Right.
You identify the 20% of your code, usually the most complex parts, the newest bits, the most changed bits, because history and data show that's where the vast majority of your defects are going to be hiding. Your testing effort is always limited, so you focus it where the risk is highest.
Let's talk about the ultimate shift-left technique then.
Yeah.
The static testing. This is before you even run the code. Is this just about finding bugs in the code itself, or is it bigger?
It's so much bigger. Static testing, so reviews of documents, requirements, test cases, and yes, analysis of the code. It's crucial for finding errors in the documentation first.
Before it ever becomes a defect in the code.
Exactly. A huge benefit is that a review can find that you have zero test coverage for a critical safety requirement, just a massive hole in your plan. But it does have limits. You hit a wall with third-party software. You generally cannot perform static testing on proprietary executable code.
That makes total sense. You can't see inside the box.
Mhm.
And during these formal reviews, say, of a requirements document, management have a very specific role to play.
They do, and it's not the technical review itself. Their key job is deciding what gets reviewed in the first place. They look at the project, they assess the risk, and they allocate the review resources to the highest risk documents.
Okay, so let's get into the heart of it. The practical K3 application stuff, test design techniques.
Right. So after you've decided what to test, the very first activity is test analysis. You're looking at your source documents, the requirements, the design, and you're asking one simple question. Is this testable? Is it clear? Is it consistent? That analysis directly feeds how you design your tests.
And I love that black box testing is so powerful because you don't need to know anything about the code. The sources say a key advantage is that you can create your test techniques regardless of the software implementation.
And the goal is always efficiency. You don't want to write 1,000 test cases if 10 will do the same job. That brings us to our first technique, equivalence partitioning, or EP.
Right.
You're just dividing all the possible inputs into groups or partitions where you assume the system will behave the same way. The idea is that testing just one value from each group is enough.
Let's use that fitness app example from the material. The app gives you different feedback out of 1,000, 2,000, 4,000, and 6,000 steps. If I just pick numbers randomly, I could easily miss a whole category.
You could.
But if I strategically pick, say, 5 inputs that hit each of those valid groups, I get much higher coverage, much faster. It's the difference between like 60% and 80% effectiveness.
And bugs love to live on the edges. They love boundaries, which is why we use boundary value analysis, or BVA, right alongside EP.
Okay.
BVA is all about testing the exact boundary values and their immediate neighbors. That's where developers so often make those off-by-one errors, so you test the boundary number itself and the number right next to it, inside and out. It's so much more likely to find a bug there than in the middle of a partition.
That is that K3 apply thinking in action. Okay, so moving from simple inputs to whole processes, we have state transition testing. This is for when a system's output depends on its history, right? Like a vending machine or a workflow.
Exactly. For a state transition diagram, the exercise is to find the minimum number of tests you need to cover every valid path between states. Even in a pretty complex system, you might find that achieving 100% coverage of all the valid transitions only takes maybe 3 test cases.
Just 3.
It forces you to be incredibly economical.
Let's wrap this section up with coverage metrics. We hear statement coverage and branch coverage thrown around. If I get to 100% statement coverage, meaning every single line of code has been run at least once, am I done?
Not necessarily, no. 100% branch coverage is the stronger metric. It's tougher to achieve.
And what does it mean?
It means that every single decision outcome, every if and every else in your code has been tested. And here's the key. If you achieve 100% branch coverage, you have automatically achieved 100% statement coverage. But the reverse is not true. You can have full statement coverage and still have huge, untested branches in your logic where bugs are hiding.
Okay, let's zoom back out to strategic planning. In a formal test plan document, there's a section called the test approach. This sounds like where the big decisions get made.
This is where you set the rules of engagement. It's your strategy document. You define the test levels you're going to use, the metrics you'll track, and your coverage goals. For example, you might insist on 100% branch coverage for the critical financial parts of the system, but maybe a lower target for, say, some UI elements.
And within that plan, we have to be really clear about the types of risk we're managing. How do you clearly separate project risk from product risk?
It's a great distinction. Think of project risk as anything that threatens your schedule or your budget. If management suddenly pulls 2 of your best testers onto another project, that's a project risk. It could derail your timeline.
Okay.
Product risk, on the other hand, threatens the actual quality or value of the software itself. The system response time is too slow or it doesn't comply with a legal standard. That's the stuff that costs you customers.
The rise of Agile seems to have really changed how teams handle these risks. It's all about a whole team approach.
It is. No one gets to say, that's not my job. The whole team, developers, testers, product owners, shares responsibility for quality. People work closely, they take on tasks flexibly, the rigid roles disappear.
And you see that collaborative spirit in things like planning poker for estimation. So, say a tester estimates a feature at 20 points of effort, but the developer and the customer say it's only 5. That's a huge gap.
You have to stop immediately. That gap means there's a knowledge gap. Someone knows something the others don't. The team has to discuss why there's no consensus. Maybe the tester is seeing a hidden integration risk the developer missed. You talk it out, you revote, and you keep going until you bridge that gap. You don't just average the numbers.
That same mindset of building from the ground up is why we use the test pyramid.
Absolutely. The pyramid mandates that you build a huge, wide base of fast, cheap, low-level tests like unit tests.
But what's the core principle there?
Efficiency and hierarchy. The higher up the pyramid you go to, end-to-end,